So in today's video, we're going to be looking at chapter 12.2, which looks at paired difference tests. This is basically incorporating everything that we have done before, but it's for a very specific type of test, and it's actually very easy to see when you would use this particular test. It comes up in things like, let's say you wanted to compare two different makes of sneaker. Okay, let's say you had two different makes and you wanted to see how well each one performed for like running. Okay, what they would do is they probably make you wear one of one type on one foot and one of one type on the other foot. Okay, and then you could wear them around just to see how they wear, to do with weather, your weight and stuff like that. Okay, just to see how well they would do, and then you can compare the two at the end. That is where paired difference comes in. Okay, it's whenever you want to compare two makes of something, or let's say you took a test and you didn't do so well, so then you took a review class to help you, and then you took the test again, and you wanted to see how well the class did the first time in the test and how well they did after they did that review class. Okay, so that's where a paired difference is used. It's used when you want to compare two things that are of the same type, and just to see how they wear through things. Okay, whether it be weather, weight, whatever it may be. Okay, so it's used a lot in experiments, and what we want to see is what the average difference is. Okay, so let's say you had a bunch of data points for the first sample. Okay, you had n of the first type and n of the second type, and you want to compare the two. Well, what we're going to do is we're going to compare the difference between each one, and then we're going to take the mean of the differences. Now, you want these two things to be pretty similar. Okay, that's what the whole point of this is. Okay, especially in like the sneaker example. Okay, you're going to assume that there is no difference between the two to start with. So whenever you conduct a test with these, you always assume that your population mean difference is 0, okay? You start out assuming that there is no difference between the two whatsoever. Then in the same way as you normally do with a hypothesis test, you're going to go ahead and you're going to take a sample. In this case, you're going to take n of one and n of the other, and you're going to conduct this test and see what happens with the sample. Then you're going to use that sample data to determine if the mean difference is in fact 0 or if in fact it's something else. Okay, so whenever you do one of these mean paired difference tests, okay, what you are doing is you're conducting a hypothesis test where you have the null hypothesis, H0, is such that the population mean difference would be 0. Okay, so we're taking a sample out of the population and testing the samples, and then we can assume something about the population mean difference. Okay, so that's the mean difference you're assuming is going to be 0, and then your alternative hypothesis could be, again, one of three things, depending on what you're trying to actually determine. It could be that you just want to show that the mean difference between the two is not 0. That would mean that the mean of one sample is different to the mean of the other sample. Okay, you're just assuming that they're completely different. With greater than, okay, if the mean difference actually ends up being greater than 0, you're assuming that the differences are skewed towards one sample. So you're saying, okay, one of my means is higher than the other mean. Okay, so one sample has a higher mean than the other. And in the same way with this less than that we have here, that would mean that one of the means is lower than the other mean. Okay. So whenever you do this, there are two different ways to conduct one of these tests. But the thing that we're kind of getting to now, we've had like t-tests, z-tests, intervals. If you're comparing two means, we're going to be getting to if you're comparing two proportions. Okay, there's a lot of tests going on here. This one is super easy to kind of recognize from the outset. Okay, you're going to see it immediately. That's because it's always laid out in the same way. What you're going to get, and I've put this like an example of it on the first page of my notes for this chapter. What they actually do is they have n observations, okay? You're going to have n of one sample and n of another, okay? And they're going to have these n data points for each one of your samples, okay? So whenever you see one of those tables where they're saying, okay, in this experiment, I'm going to be comparing this sample to this sample because I want to see what happens with the mean difference. Whenever you see that and you see a table, you know that this is the test that you need to use. Okay, so it's super simple. You're basically watching out for a table. Okay, as I said, there's two ways to do this. Okay, the first way works with any one of these three alternative hypotheses, whether it be two-sided or one-sided, whether that be left or right-tailed. Okay, and the way that you do this is to run a t-test on the differences. Okay. If you look at page 1 of my notes on the Google Drive for 12.2, you will be given the first 3 columns of that. They may be done as rows, but you'll be given the first 3 columns. You'll have the number of the observation, and then you will have n of the first sample and n of the second sample. Okay, so you'll have n data points for each one of the samples. You will then have to go ahead and figure out the difference. Okay, now this is where you have to read the question, because they are going to tell you which way to take the difference, whether to do sample 1 data point minus the sample 2 data point, or whether to do it the other way around. So please read the question when you do this. Otherwise, you're going to end up with the wrong answer, because when you add all of these together, it's going to end up being the wrong answer. So please make sure that you get this the right way around. So you're going to go ahead and figure out those differences. Okay, between sample 1 and sample 2. In this case, I've done sample 1 minus sample 2. Okay. What you then want to do is to look at the mean of those differences. Now, we've only got a sample of n data points for each one of my samples here. So I've got 2 populations. Let's say 2 makes a sneaker. And what I want to do is I want to compare the 2. So I've taken n of one sneaker and n of another sneaker. And what I'm doing is I'm comparing the data points. Let's say that I had n people, okay? I had n different people that wore one of each type of shoe. Okay, they wore one of sample 1 and one of sample 2. So those n observations relate to the n different people that were doing this experiment. And then sample 1 is one sneaker, sample 2 is the other sneaker. Okay, so you calculate this difference, and what you're then going to do in your calculator, put that list of differences in your calculator. Okay, so you go ahead and put that list of differences, once you've calculated them, into your calculator. Now, another way that you can do this, okay, when you put that list into your calculator, because there's always a worry that you're going to get a computational error somewhere where you've just added wrong somewhere, and especially during a test situation, when you're quickly typing stuff in, everyone worries that they're going to make a mistake doing this. What you can actually do is type in the exact data that they give you. So let's say in list 1, you put all of the n data points for sample 1, and in list 2, you're going to put the n data points from sample 2. If you then go to list 3 and go to the top, what you can actually type in at the top where it says list 3, just do equals list 1 minus list 2, or list 2 minus list 1. Okay, so you could just do equals and then L2 minus L1 or L1 minus L2, and it will do those differences for you. Okay, so you don't have to worry about any computational error. So that is another way of doing it. So just type sample 1 into list 1, sample 2 into list 2, and then in list 3 you could just say that list 3 at the top is equal to list 2 minus list 1, or list 1 minus list 2, depending on which way they tell you to do the differences. Okay, so once you've got that into your calculator, that's always the first step regardless of what you're doing. Always get that list of differences into your calculator. Now, what you want to do is you want to run a t-test on this list of differences, okay? What that t-test is going to do, before when we've done this, we've gone into stats tests and t-test, and then you've always put in the statistics that were given to you in the problem. Now your input is data, okay, your input is that data list. Because normally when you run a t-test always asks you for the sample mean, the sample standard deviation. Okay, t-test means you've got a sample standard deviation, not a population standard deviation. So you've got the sample standard deviation, and it will ask you all these different things, okay? When you input a data list, it's going to calculate all those things for you. You don't have to worry about what that mean of those sample differences is. You don't have to worry about what the standard deviation of the sample differences is. It's going to do all of that for you. So what it's doing when you run a t-test on that list of differences, okay, so you're going to run a t-test on the list of differences. Okay, when you do that, okay, it's going to go ahead and do a t-test exactly like before. So you have to tell it, let's say, what your alternative hypothesis is. So you have to tell it whether it's two-sided or one-sided, whether you've got a greater than or a less than, okay? So you have to go through and do that. You're always assuming in this case, okay, that your population mean is 0, okay? You're always assuming that there is no difference between the two samples until proven otherwise, okay? So that is why your null hypothesis is always that the population mean of the differences is 0. When you've got a population mean of the differences being 0, what that is saying is that there is no difference between the two makes of whatever you have. There is no difference whatsoever. So if I were to take those differences, okay, they would all be scattered around 0. So the mean would be 0. So that is one way that when you put it into your calculator, please make sure that your population mean that you're trying to prove that it is or isn't is 0. Okay, your population mean is 0. Everything else will come off of that data list. Okay. Now, sometimes, actually, I'll say one thing before. When you run this t-test on that list, as I said, you make your population mean 0. It will get all the sample data from that list. You can then, when you run this, go ahead and do two different things. The first way, as always, you can compare the p-value that comes out of this to the significance level that they wanted you to conduct the test at. Okay, so in the problem, as always, they'll say conduct the test at the significance level of alpha is equal to 0.05. Okay, so you can go ahead and you can compare the p-value that you get out on your calculator to that significance level alpha. Okay, if p is less than alpha, you're going to reject the null hypothesis. If it's greater than alpha, then you're going to fail to reject the null hypothesis and you're going to say our mean difference is 0. Okay, so that's same as always. But the second way that you will sometimes have to do this is the long way. Okay, where again you write down what your null and alternative hypotheses are, you find your significance level, then you find your test statistic, then you find a critical value, you compare your test statistic to the critical value, and then you can go ahead and determine whether to reject or fail to reject the null hypothesis. The thing with this chapter is sometimes they will ask you for a critical value. There is a simpler way of doing it rather than you typing some stuff into a calculator, and that is by using a table. If you are on Hawks and you decide to use this method, you can go ahead and use the P and the alpha and do it that way if they just say to you, conduct the test. But sometimes they will say to you, what is the test statistic? What is the critical value? Go ahead and then figure out whether to reject or fail to reject the null hypothesis. So the second way, do this the long way. Using test statistic. Okay, so this is the exact same thing that we have done previously with other chapters, but now we're dealing with the differences and not the data points. Okay, so you're using a test statistic and a critical value. Okay, I'll tell you what the test statistic and what the critical value are, just so that you have it. Your t-test, when you do a t-test on that list of differences, it should actually give you the test statistic. Okay, so your calculator, when you run a t-test, will give you the test statistic. It will not, however, give you a critical value. That is something that you will have to find. The test statistic, okay, in this case, we are running a t-test, okay, because we don't have any population standard deviations, okay? We don't know the standard deviation of the differences of the population, okay? So we don't have that population standard deviation. The population differences and taking their standard deviation, that's not a thing here, okay? We don't have that. We only have this sample data. We only have the sample differences. So we can get the standard deviation of the sample differences. We just don't have the standard deviation of the population differences. So we know that because we've only got the sample data and not the population standard deviation, we know that we have to use a t-test. So your test statistic in this case is t, okay? Now, it's exactly the same as what you have seen before with the means, okay? Because what you are doing here, you're taking a sample mean, but it's the mean of the sample differences, okay? So it's a sample mean, but just of the differences rather than of the data points, okay? So this test statistic is going to have the exact same form as the test statistic for the sample means, okay? I'm going to write all of this out. Remember here, when we did this, when you are looking at the test statistic for the sample means, okay, it was always the sample mean minus the population mean divided by the standard deviation over the square root of the sample size. Two things to note. Number one is that you're dealing with the mean of the sample differences here. So this is not just the sample mean of the data points, okay? So it's not just the mean of the sample data points. You are dealing with here the mean of the sample differences, okay? So we've taken the data points, found their differences, and that's what we're taking the mean of, okay? So it's slightly different in form. So this would be, this part here is the sample mean of those differences. So taking that sample data and you've taken that list of differences for those n data points, for sample 1 and sample 2, that is the mean of those n differences, okay? Population mean is 0. That's what we're assuming it to be, okay? We're assuming that there is no difference right now between population 1 and population 2 until proven otherwise. This here is your sample standard deviation. Remember, when we did a z-test, this was the population standard deviation. But here we don't have the population standard deviation. We don't know what the standard deviation of the population differences here is. We only know what the sample differences standard deviation is, okay? And then you divide that by the square root of the sample size. So this actually reduces down to the mean of the sample differences divided by the sample standard deviation of those differences over the square root of m. Okay, so that is your test statistic if you do want to figure it out by hand. But as I said, when you run a t-test on that list of differences, it's going to calculate that for you. The other thing is the critical value. Now, I've told you before how to find the critical value, and it's to do with that significance level alpha. Okay, if you have an alternative hypothesis that has a does not equals in it. So if you have your alternative hypothesis is that the mean of those differences is not 0, then you end up with a two-sided alternative hypothesis, okay, where you've got one danger zone here and another danger zone here. And the way that you found this was to say, okay, I've got a significance level of alpha, so in this case, the area under that part of the curve would be alpha over 2, and the area under that curve would be alpha over 2, okay? Because we want to reject our null hypothesis alpha percent of the time. So alpha would be a decimal, but let's say alpha was 0.05. That means we want to reject our null hypothesis 5% of the time. But in this case, I've got a two-sided alternative, which means that I need to break up that 0.05 to either side. Okay, so that's with the significance level of alpha, and then you would have 1 minus alpha would be in the middle. Okay, then your critical value, okay, you can find the critical value there and there. One would be a negative of the other. So this critical value here is just the negative of what is here. Okay, and the way that you found those was by using inverse t. Remember, we're dealing with a t distribution here because we're only dealing with sample data. So you would go ahead and do inverse t, and you plug in the area to the left of the critical value. You could go ahead and find the negative version of it by just plugging in an area of alpha over 2, or you could find the positive version of it by plugging in your area would be like 1 minus alpha over 2 would be the whole area to the left. So you could go ahead and plug that in and figure out the area, and it would also ask you for the degrees of freedom. Degrees of freedom is always the sample size minus 1. Okay, so you can go ahead and do that and figure out the critical value. And then if you had instead a one-sided alternative, okay, I'm going to do this for a greater than. That would mean that you had a one-sided alternative. Because it's greater than, it means that you're dealing with this end up here. So your critical value would be this point here, where you had alpha being your significance level as an area there. If you had a less than, then it would be an area of alpha over this side if you had that the mean was less than 0. Okay, so it's exactly the same as what we've done before. Okay, you go ahead and find out that critical value using inverse t. So the easier way to find the critical value is to go to Hawks, and you'll see whenever you do one of these homework problems, the problem will be at the top, and then you normally have where you type in your answer right underneath it. In between the two of those on the right hand side will be a button that says tables. If you click on that, on the left hand side there is something that says T table. What that will do, if you click on T table, it will ask you for area in one tail or area in two tails. All that looks at is this example like we have here. Do you have a does not equals alternative hypothesis, or do you have a greater than or less than alternative? Okay, so whichever one of those you have, click on whether it's two-sided or one-sided, and then it will come up with this table, and all you have to do is find the significance level and find the degrees of freedom, match it up, and that will tell you the critical value. So it's actually way easier than trying to deal with like areas and stuff like that. It's actually much quicker to use these tables. It's the only time that I will really tell you to use tables, apart from in chapter 16, because sometimes it can get kind of confusing. But whenever you need a critical value, if it asks you for that in chapter 12.2, and you need that critical value, go to tables, T table, and then you can, whatever your degrees of freedom are, which is the number of sample points minus 1. So the degrees of freedom is always n minus 1. So if you have n pairs, just subtract 1 from that, and that will give you the degrees of freedom. And then on the top is like 0.1, 0.05, 0.025. That is alpha, the significance level. So whatever your significance level is, match that up with the degrees of freedom, and that will give you the critical value. The only thing I have to warn you about is when you have an alternative hypothesis that looks like that, so it's a less than. In this case, when you draw out your curve, okay, it's a less than problem. So we know the tail is going to be to the left, which means that your critical value is going to be over here. 0 is in the middle. That means your critical value is negative. So please keep that in mind when you do this, okay? If you ever have an alternative that has a less than, you're going to have to make your critical value that comes up on the table, make that negative, okay? Because they will only deal with positive values here. So it's fine if you've got a does not equal or a greater than, but if you do have a less than, make sure you make that value negative because it will always give the positive value in the table. Okay. So you can then compare your critical value to your test statistic. And if your test statistic, let's say in this example, if your test statistic T fell in here, then you would reject your null hypothesis. If it fell somewhere over here where is not in that danger zone, so that would be your danger zone because it's a less than problem, which means that the tail is to the left. If T fell over here, then it means that you would fail to reject that null hypothesis. Okay, so it's exactly the same as normal. It's just finding the critical value in the test statistic and comparing the two. But as always, unless they ask you specifically for the test statistic and the critical value and for you to go that way, the much easier way is to come back here and just to compare P and alpha from the t-test. Okay. But if you do have to go the long way, remember that the calculator, when you run a t-test on those differences, it will give you the test statistic for the sample mean difference. Okay, it will calculate this value for you. It's just the critical value that you're going to have to get on the table. Okay. Now, there is another way of doing this if you have a two-sided alternative hypothesis. So as normal, okay, remember back when we did just normal data points and you were doing this. If you had a two-sided alternative hypothesis, another way to conduct this test is to do a confidence interval, okay? That is still perfectly reasonable to use in this case. So if you have a two-sided alternative, so your alternative is such that the mean difference for the population does not equal 0, then you can use a confidence interval. So you can do it the other way, that's totally fine. You do not have to use this way for the two-sided alternative. You can absolutely do it this way or the short way. Okay, so please don't feel like you have to do it this way, but sometimes they may ask you for a confidence interval, so just be aware of this. If you have a two-sided alternative, then you can use a confidence interval to determine whether or not to reject the null hypothesis. Okay, so the confidence interval in this case it's very, very similar to a t-interval. Okay, it looks exactly like a t-interval. So you have your sample mean difference plus or minus this t-value times the standard deviation over the square root of the sample size. Okay, you can go ahead, this is just done using a t-interval on the list of differences. So if you have that list of differences in your calculator and you have a two-sided alternative, what you can do is go into your calculator and instead of going to t-test, go to t-interval. Okay, it's still in the same menu. Go to t-interval and run it on data where you're using that list of differences. So instead of stats, you're using data. It will calculate the sample mean difference. It will calculate the sample standard deviation of the differences. Okay, it will do all of this for you. It will calculate that t-value. Okay, you can also get that t-value from the critical value that you get on those tables. So if it asks you for that t-value, that is just that critical value. Okay, so you can go ahead and use that. This is just another way to do the two-sided alternative. Now, the way that you can see whether to reject or fail to reject that null hypothesis, you want to know if your population mean lands in this interval. Well, your population mean is 0 because you want the difference, the population mean difference, to be 0. So if 0 lands in this interval, if 0 does land in this interval, okay, that means that we can assume that that mean difference for the samples is close enough to 0. That means for your sample, if 0 lands in this interval, for the sample, it must mean that those differences are close enough together that the sample mean difference is roughly 0. That means that we can therefore assume that our population mean difference must be 0. So if 0 lands in this interval, you fail to reject the null hypothesis. Okay, but if 0 does not land in this interval, okay, if 0 doesn't land in the interval, that must mean that our sample mean differences must be far enough apart that we cannot assume that those samples are going to be the same, which means that our population mean difference cannot be 0. There is no way, so we're going to reject the null hypothesis. Okay. So it's exactly the same as when we've used these confidence intervals before. Okay. On my notes, I have a couple of examples that you can go ahead and try out. They're very similar. They are actually homework problems that I got from the practice section. So the first example, it's given you two populations. This is at the end of page 3 on my notes. It gives you two populations. And what it wants to know is to find the 90% confidence interval for the true difference between the population means. Okay, so all you're going to do, it's given you 7 data points for each of the populations. Okay, they're actually samples from the populations. You're going to go ahead and you can find the difference between the two. Now notice it is said that the difference is the population 1 entry minus the population 2 entry. So I'm doing sample 1 minus sample 2. Make sure you get it the right way around depending on what they tell you in the problem. So you must read the question. Okay, so you do the first entry minus the second entry all the way along. That's going to give you the differences. So in this case, let me quickly write this out. So you've got sample 1 and sample 2, and they've given you 34, 34, 34, 20, 27, 18 and 41, and then 48, 25, 40, 18, 24, 23 and 27. Okay, you then, it gives you in the problem that the difference is the population 1 minus the population 2. So in this case, when you do 34 minus 48, you're going to get negative 14. 34 minus 25 is 9. 34, that's going to give you negative 6, 2, 3, negative 5 and 14. Okay, you can then go ahead and put this list as a list in your calculator. Okay, so go ahead and put that as a list in your calculator. Now, you could just go ahead and run a T interval on that list. So if you go to, once you've got that list in your calculator, go to Stat, go across to Tests, scroll down to option 8, which is a T interval. Okay, now you have input data. So your input is data. The list that you put in for your data goes in list. Frequency is 1, and the confidence level on here, it says it's 90% confidence interval, so your confidence level would be 0.9. You go ahead and calculate, it will give you that confidence interval. Okay, now if 0 falls within that confidence interval, whatever that interval may be, if 0 is in there, we know that these values are all close enough together that we can consider them to be the same, and therefore their means are going to be the same. So the mean difference is going to be 0 if 0 falls within that interval, because it means that all of these data points are going to be close enough together that the sample mean difference could be 0, and therefore the population mean difference we're going to assume could be 0. Okay, now if 0 falls outside of that range, okay, that means that we can no longer consider our population mean difference to be 0. This means that these data points would be far enough apart that the sample mean difference isn't 0, therefore our population mean difference can't be 0. Okay. Just as a heads up, in this case, the degrees of freedom, if you did ever have to calculate that, the degrees of freedom in this case would be 6, because it's 7 minus 1. You've got 7 data points on each one. It calculates all of that for you, but the degrees of freedom would be 6 because it's 7 minus 1. In this second example that I have on page 4 of my notes, it's about an SAT prep course. So they made people take this test before taking a prep course. Then they took the prep course and then they tried the test again and saw what the difference was between the scores the first time they took it and the second time they took it. So again, they've used 7 students here. And they've looked at the score on the first SAT and then the second SAT after they'd taken that prep course. So it says that they want to know whether it improved, okay? And they said that the difference is the verbal SAT score prior to taking the prep course minus the verbal SAT score after taking the prep course. So that means that they're taking the first test minus the second test, but they want to see whether they've improved. So let me quickly write this down. So this is the first SAT score, second SAT score, okay? And there's 7 students that took this. So they had 380, 410, 400, 410, 360, 550, 550. Then I've got 410, 510, 430, 390, 590, and 600. Oh, I've missed one off here. Let me try that again. So I've got 410, 510, 430, 480, 390, 590, and 600. Okay. So for my 7 students, this is what they got in the first test and then the second test. They've said that the difference, okay, is going to be the first score minus the second score. And they want to see whether the test scores improved. Okay. Because they want to see whether the test scores improved, do we expect these differences to be positive or negative? Well, if we're doing the first score minus the second score, where they've taken this prep course before getting that second score, before taking that second test, we would expect this difference to actually be negative, okay? Because the first score would be lower than the second score. So your null hypothesis, as always, is assuming that that mean difference is 0. But your alternative hypothesis, okay, the mean difference in this case, if we're doing the first score minus the second score and they want to see whether the test scores improved, that would mean that we are looking at whether that second score is higher than the first score, which means that that would be your alternative hypothesis because you're assuming that that difference would come out negative, okay? Now they've said that alpha, their significance level, is going to be 0.1. Then you can go ahead and run this. So you can either go ahead, the first thing that you always have to do is to find your differences. So in this case, doing the first minus the second, you're going to get negative 30, first minus the second, negative 100, negative 30, negative 70, negative 30, negative 40, negative 50, okay? You can go ahead, put those in your calculator, and then you can run a t-test on this. We are dealing with a one-sided test here. Your alternative hypothesis is one-sided. So because we have a one-sided test here, we cannot run a confidence interval on it. We have to use just a standard t-test. It's the only way we can do it. So you're going to run a t-test on this list of differences, okay? It will give you the test statistic, it will give you the p-value. So you can either compare the test statistic to the critical value using the tables, or you can compare the p-value to this alpha value, and you can see whether to reject or fail to reject the null hypothesis. So once you've set the problem up and you figured out the differences and you figured out what your null and alternative hypothesis should be, depending on what they tell you in the problem, the rest of it is exactly like what we've done before. It's just a case of getting this thing set up correctly. Go ahead and try some of these out in the homeworks. I know that it can get kind of confusing on this, but once you've got the hang of this and dealing with one-sided and two-sided like we have before, and making sure that you are using that list of differences, okay, you're not using the data list, you're using the list of differences, putting that list in your calculator and then running all of these tests or confidence intervals on that list, after that it's exactly the same. But it's just a case of getting through that part and then the rest of it is exactly like what we've done before. But please remember, you are using t-intervals and t-tests here because we don't have that population data. We only have the sample data. Okay. Go ahead and try the homeworks. If you need any help, please let me know, and I will be more than happy to help you out. And I will see you in the next video.